Welcome to Module 8B in my Introduction to Tensors for Non-Mathematicians online course here on YouTube. The title of this, like the last, is Linear Maps. Now, why split this up into two parts? Essentially, it was getting very long. I found a good stopping point and decided it would be optimal to split it up. I haven't given them different numbers, for example, Module 8 and Module 9, because I don't think they really stand alone as compared to many of the other parts of this online lecture series. So I'm going to give essentially very little introduction here because I don't think it's optimal for viewers to watch this Module 8B without seeing the first part. So my advice is, if you've happened upon this video, want to learn more about linear maps, go back, check out part 1, part A of this lecture, and then return to this one. In the description below, you'll find all the information you need, including links to the previous as well as the next lecture, and some information on the accompanying text. So next, we're going to discuss how the linear map may be generated from the tensor product of a vector and a covector. If you remember, we said that the rank 1 tensors, the primal and the dual vector, those were the last ones whose components we can designate or define as purely covariant or contravariant because they're rank 1. For the linear map, the components are going to have contravariant and covariant components. We can formalize that as the tensor product of vectors and covectors. So I know we're saying a lot here. Let's hold off before we try to explain too much. I first want to talk about the concept of a tensor product. So the tensor product is discussed at length in the text that I'm posting, hopefully very soon. Hopefully it's already up. But for now, we're not going to discuss it at length in the PowerPoints. For now, let's just assume that it's sufficient to say the tensor product, which is indicated by this operator, is the tensor product of a row and a column-oriented array, as shown down here. It generates a matrix with a height equal to that of the first and a width equal to that of the second. And what we essentially do is distribute all the products. So if you look down here, forget about this pure matrix for a second. We can say a matrix is equal to the tensor product of some column-oriented array V and some row-oriented array gamma. All right. Now, the height of the column-oriented array is N1, so we see the same height of the matrix. The width of the row-oriented array gamma is N2, so we see the width is the same. And the individual elements are simply taken from those permutations or different combinations of V1, V2, gamma 1, gamma 2. So you see element 1, 1 is the product of V1, gamma 1. Element M1, 2 is the product of the first V and the second gamma. Down here you have product of second V and first gamma, second V, second gamma. So you can think of M, K, P as equal to, for this case exactly, V, K times gamma, P. Now remember, again, V is strictly contravariant, so it only has a contravariant index. Gamma is strictly covariant, so it only has a covariant index. So hopefully this provides enough of an explanation for the tensor product to allow us to move forward. Now, a pure matrix is one that may be generated from the tensor product of a single row and column-oriented array, as shown down here. So this is a pure matrix, the tensor product of a single column-oriented and single row-oriented array. And we've already talked about how the various products are performed. So a pure matrix may be defined as, and this is actually the equation we just drew, right? Every element, M, k is equal to the product of the mth element of the column-oriented and the kth element of the row-oriented arrays. A pure matrix may be represented as the tensor product of one column and one row-oriented array. So note that pure matrices, pure coordinate matrices, are rarely employed for linear maps because the form is somewhat limited. Okay, impure coordinate matrices, which is really just the opposite of pure, meaning it needs more than one and more than one column oriented and more than one row oriented array. So the impure coordinate matrix generates an output that may vary in both length and orientation, making them more interesting and useful, whereas the pure matrix really only allows us to vary the length. So it's like it allows us to scale it, but it doesn't allow us to perform more advanced manipulations. So the impure matrix, unlike the pure matrix, cannot be defined in this way. We cannot use a single row-oriented and single column-oriented array. Trying to do so will yield an inconsistent solution definition for at least one element of the arrays used. So there are certain matrices that we can create that no matter what values we employ for the column and the row-oriented array, we cannot generate that resultant matrix. Okay, and if we can't do that, then it's called an impure matrix. Now, why am I talking about this? Because we're going to see that the coordinate matrix of our linear map type tensor will most likely be impure. Again, because we want to have the ability to vary orientation as well as length. So here's an example of an impure matrix. I'm not going to go through and prove it, but essentially, right, you cannot get these values of 3, 300, 6, and 1800 with some consistent set of values over here. There will always be one product which is inconsistent. Okay, so let's pause our discussion of the coordinate matrix for a linear map type tensor, and let's talk about the basis set, and then we're going to come back and put it all together. I know we're in the middle of this discussion and perhaps everything's not very clear, but we're gonna clear it up. Okay, so we observed previously that the primal basis set contains multiple vectors. The dual basis set contains multiple covectors. So we're seeing a trend here, right? The basis set of a tensor is composed of algebraic objects with a similar structure. Okay, the primal basis set is associated with a primal vector, and so that set is composed of vectors. The dual basis set is associated with a dual vector or a covector, and so it's composed of covectors. So our linear map, we expect the basis set to be composed of matrices. So that's what's said right here. As such, we know that the basis set associated with a linear map contains multiple linear maps, or we can refer to them as matrices. The objects contained within this set may be defined via tensor product, again, same thing we saw before, of the basis associated with the input and output vectors. The result is an impure linear map coordinate matrix. If you saw in one of the previous slides, we said that the basis set of the linear map can be generated by something like this. Now, what does this mean? It's saying we're taking the tensor product of some primal vector basis set and some dual vector basis set. And so this is how we are going to generate the basis of our linear map type tensor. We already saw that if I can find it, we already saw that the tensor product of a primal vector and a covector, or a column-oriented and row-oriented array, will generate a matrix. So this makes sense, okay? The form we're going to use to generate the matrices that populate the basis of the linear map, it's going to follow a very similar form to this. All right, so now let's dive into that. So we're going to use a little bit of an example to demonstrate this. Let's start off by considering some primal and some dual basis set as defined below. We're not going to give these subscripts right now. We're actually not going to talk about where they come from. They exist. We have some primal basis set B, which both of these are standard basis, or we can call them orthonormal basis, which is convenient for these types of discussions. And so this is a covariant array. So it's a row, and we have these covariant indices. Then we have the dual basis set, and that is a column-oriented array, and so it's contravariant, and we use these superscript indices. Now, let's say we want to take the tensor product of these two. All right. There's really 4 different tensor products that we can define, okay? Assuming that we're going to consider each basis vector and covector individually. The first permutation would be B1 times beta 1. Then we have B1 times beta 2. So before we move on though, let's explain what this means. So B1 is taken directly from right here. And that's why we have a 1 and then a 0. Beta 1 is taken directly from right here. And so that's why we have a 1 and then a 0. And so the elements, the resultant matrix, is simply just in this spot, we have 1 times 1 gives us a 1. In this spot, we have 0 times 1 gives us a 0. In this spot, we have 0 times 1 gives us a 0. And in this spot, we have 0 times 0. That gives us a 0. The second permutation, the 1 moves to the right. The second row remains unchanged. The first row, we see the 1 jumps to the right-hand side. So all four of the permutations are shown here. We have B1 beta 1, B1 beta 2, B2 beta 1, B2 beta 2. And these are going to be the standard basis of our 2x2 linear map. And it's simply taken from the tensor products of these. Now, generally, if we don't include the indices, what I can do is represent this whole thing as this, right? So when we don't include the indices, that's a representation of the entire set. So we observed previously that the primal vector, and this is a little bit of repetition, but that can be good sometimes, is defined by the linear combination of its basis vectors, right? We saw that a primal vector is equal to the basis set times a coordinate array, no arrow hat, which can be expanded to look like beta 1, or sorry, not beta, B1 times V1 plus B2 times V2, and then it goes on. So that's a linear combination of its basis vectors. We can do something similar for the dual covector. It's defined by the linear combination of its basis covectors. For both, the coefficients of that linear combination are defined by its respective coordinate arrays. And, spoiler, for the linear map, we're going to use the coordinate matrix. So we see a similar constructor exists for the linear map. The next slide generates a linear map type tensor from its associated coordinate matrix, as well as vector covector basis pairs. Now this is specifically what we discussed on the previous slide. Right, so we combine these two as a linear combination of all the vector covector basis pairs. And this is a description of the basis set for the linear map, which is really just taking all of these or all of these and collecting them together in a single construct. So we have B1 beta 1, we have B1 beta 2, B1 B2 beta 1. Anyway, it goes on and on and on. So let's look at that. Let's stick with our 2x2 example for right now. We want to create some tensor M bidirectional arrow hat. And so first, let's forget about the blue for a second. Let's just create a sum of the 4 bases. Now, each one of these bases have a similar structure to the resultant tensor. They'll have the same rank and the same size. Okay, and these are all matrices composed of 1s and 0s in the purple. We defined these previously. To create our tensor, we multiply them by the corresponding elements of the coordinate matrix. And so what we end up with is a linear combination of matrices, which yields our tensor. And here is simply a summation-based form. Now, you may be asking, well, didn't we already define this? Didn't we already say that M bidirectional arrow hat was the same as B pre-B? If I'm going back to the notation that we used previously, times matrix M times B pre-A inverted. So what's going on here? Why do we have 2 different definitions? Now what we're going to see is that this is good for a linear map only. As we get into higher rank tensors, it's going to become increasingly difficult to represent our coordinate construct matrix in this way, and it's going to become easier. Well, it's only going to be possible to define it in terms of this linear combination. So anyway, to make a long story short, these 2 are equivalent. We're not going to show that explicitly, but you can derive that equivalency. Also, to give a quick note about the summation form, we're going to see very soon that as we move on to higher ranked tensors, this expanded form, something like this up here, becomes less and less practical, and the summation form becomes more and more useful and more practical for several different reasons. First off, these algebraic objects will get pretty big, and also as we move from the linear map to the bilinear form, and now we are mapping from multiple sets of primal vectors, we have to worry about how the contracted product is going to be applied with respect to certain ranks. I don't know if that makes sense to all of you, but anyway, the summation-based form, we will begin to lean on that more and more as we move forward. So let's ask a question, though. What are these, right? What is the B? What is the beta? If we look at this form, we can kind of get a hint, right? We can see that the B and the beta are probably going to be coming from the basis sets associated with the primal vector input and primal vector output. But how exactly are those going to line up? So we're asking the question again, how are the primal basis and the dual basis sets defined? How do they relate to the input and output vectors? We already suspect that there's a relationship there. And to answer this question, we're going to look back at one of our previous equations. And this is the one that we actually just referenced. We observed that the coordinate matrix M was equal to the inverse of the output basis set times the linear map tensor times the basis set associated with the input. And if we take a look at this, we can kind of see what gets inverted and what doesn't. Actually, as opposed to using this form of the equation right here, I think it is more evident if we invert it and look at this form, B pre-B times M, no arrowhead, times B pre-A inverted arrowhead. So it makes sense that this B pre-B, or the basis associated with the output, would take the place of the primal basis set. This right here is inverted. And so that changes the form, or it allows us to change the way we visualize the form. And so we'll see that beta is equal to our inverted input basis set. All right, and that lines up, that agrees with this equation down below. So the dual basis of a linear map is defined via inversion of the primal input basis set. This corresponds to this, and this corresponds to this. This makes sense because we expect for our mapping to be tuned, let's say tuned to a desired relationship between the input and output primal vectors. So we create a map, a linear map, which is designed to bridge the gap between these two, this primal space A and primal space B. And as such, it has to use the same basis as primal space A and primal space B. Those two are inherently linked. And so the basis set for the linear map coordinate matrix, or we could just call it the basis set for the linear map, is defined as shown right here. So it's the tensor product of the primal basis associated with the output vector times, or tensor product, times the inverted primal basis associated with the side A, or the input vector. And we can visualize this inverted primal basis set as being a dual basis set in terms of the way that we divide up the elements or the sub-elements. And we're generally just going to represent these various permutations. So we've looked at this before. It's first basis times first basis, first times second, second times first, on and on, right? This will be a column, this will be a row, so that gives us a matrix. But generally there's no ordering or structure to these bases. It's just a list contained within the curly brackets, and we know that some linear combination of those will generate our desired tensor output. So here's two different ways of looking at the calculation or the generation of the tensor, right? We can look at it as the product, this is the contracted product, of the primal basis associated with the output times the coordinate matrix times the inverted basis associated with the input. Now, if you note, we're using this this bracketed subscript again. If you remember, we introduced that a couple minutes ago. And what this says is that this coordinate matrix M is defined in terms of these two bases. Of this basis set, which is then in turn defined as the tensor product of the two individual bases. Now, this is a form, well, both of these actually are forms that are going to be specific to a linear map. As we get into higher rank tensors, it's going to be more difficult to present it in this way. Anyway, moving forward, we also have a summation form which states that element M superscript K subscript. So M is the contravariant index, K is the covariant index. With respect to this basis set times individual elements from the individual basis. We take the summation of all of that, and it gives us our resultant tensor M with the bi-directional arrowhead indicating that it's a tensor. Now, if you want to see this type of calculation worked out, element by element, you will have to take a look at the text, which either is available in the description below or will be available very soon. It's a little bit much to do here for the PowerPoint. So lastly, well, not lastly, but we're getting close to the end here, some terminology. Little bit of a review, but I want to make sure we're clear on these terms. So we have a linear map type tensor, M, with the bidirectional arrowhead. It describes the mapping between two vector type tensors who reside in their respective primal spaces. As a tensor, M double or bidirectional arrowhead is invariant to change of input or output basis. Then we have the linear map coordinate matrix M. It defines the mapping between the two column type arrays, coordinate arrays associated with VA and VB. So we have V pre-A. Again, we're using the pre to indicate that we haven't applied any transform to it yet, and V pre-B. So tensors map tensors, and matrices map matrices, or you could say map arrays. The basis of matrix M must agree with those of the arrays V pre-A and V pre-B. And this is similar to what we saw over here, right? Our coordinate matrix is defined as the tensor product of the basis sets associated with the inputs and the outputs respectively, with one being inverted. So matrix M is variant with respect to covariant change of basis in either the input or the output vectors. So if we have an expression that looks like this, all right, and we decide to update that, so I'm going to call this V post B, right? We need a new matrix, which I'm just calling M2 for the sake of it, in order to complete that expression. We cannot use the same M from above, and the same thing would apply if we were to redefine V pre-A as V post A. Essentially, any change of basis that's applied to either the input or the output, if we want to maintain the same mapping in the coordinate form, we need to redefine our matrix M. And so this is one of the main things we're going to talk about in the next section, not to get too far ahead of ourselves, but how do we apply a transform to this coordinate matrix here? And then, since we're talking about terminology still, what is the basis set of a linear map? It's defined as the tensor product of the primal basis set associated with the output times the inverted primal basis set associated with the input. And right, it describes the set of bases associated with the linear map type tensor. And we can create our linear map type tensor as, right, and I probably didn't want to write all of this, but since we're already going down this path, right, the linear combination of the individual basis matrices times the coordinates that are associated with them. The next module, and that's not really a part 3 to these two because it can stand alone, demonstrates how the components of a linear map respond in a special and predictable way to covariant change of basis applied to either the desired input or output. That phrase, special and predictable way, should sound familiar because we used it as part of our definition of what a tensor is in a previous module. Furthermore, I'm going to take one of the MATLAB scripts from the text, again to be published soon, and use it to reinforce much of the theory presented in the previous two half modules. For example, we're going to calculate the tensor, a linear map type tensor, in terms of its coordinate matrix and basis. Now, unfortunately, this is probably the only MATLAB script from the text that I'm going to discuss in these YouTube videos, as explaining the scripts, especially line by line, can be difficult in this medium. So if you're interested in these scripts or using MATLAB to reinforce your understanding of tensors, I hope you'll consider picking up the text. In short, the next module defines the forward and backward transforms associated with linear maps, as well as how they may be implemented in MATLAB. A link to the next lecture is available in the description below, again, or will be available soon. I look forward to reading your questions and potentially corrections in the comment section.